Алло, ребята, вы слышите меня? Моргните, помахайте рукой.
Да.
Да, привет, все нормально слышно.
Он сказал, что он сейчас джойнит нас. Я тогда представлю его. Hi, Kevin. Can you hear me? Hey, Kevin, can you hear me? I cannot hear you, man.
Okay, hello.
Hey.
Привет.
Hi. Hi. Well, okay, guys, let me introduce you to Kevin Waters. I worked with Kevin before. He is an expert on search engines. Well, generally speaking, he is a great guy. And I think we all appreciate him coming to us and tell us about the search engines. It's a cool subject. Oh, by the way, Kevin also, if you can see him, I think at the corner of his apartment or his house, you will see the robot.
Yeah, his head's off right now.
Yeah, but I guess he will talk about that as well. So, Kevin, here we have guys, some of them employees of Reactor, and some of them students in one of the Ukrainian university. So it's a good audience, and here we go.
Great.
I'll make you a presenter.
Sure, I have a pretty small little slide deck where we can kind of talk about search engines. Nothing too fancy. I'm hoping that, maybe this will just start as a place where we can begin a conversation about it, about the industry, about technology, and all that sort of good stuff.
Okay.
So let me just make sure you can. Are you seeing the slide deck? Are you seeing my screen?
Yeah, now we do.
I think I want to share this one here instead. You see the slide deck, search engine introduction?
Yeah.
Okay, cool. All right, so I don't know how familiar you are with search engines and search technology. I'll give you a quick background on myself. So I'm the founder of KMW Technology. I've been working with search engines now since about 2002, where I was a senior solution architect at Fast Search and Transfer. That was a Norwegian search engine company that had created and powered a site called alltheweb.com way back in the day. They were purchased by Microsoft and became the search that powers SharePoint. After that, I went on as one of the original founders for another search startup company called Ativio, who also was in the search space. And they had built their platform off of a technology called Lucene. We'll talk about that more. And then in 2010, 7 years ago, I went off and formed my own consulting company where really we just focus on big data search solutions for people. So one thing to say is, what is search? And I think that we all have a good appreciation for how amazingly easy Google has made it. You just type in some keywords, it's searching through 18 billion web pages and generally returns those search results in a number of milliseconds. So from a computation perspective, it's a real good question of how can they do this, right? I mean, certainly they've got a lot of servers and all that stuff, but we're still talking about, hundreds of thousands of queries coming in per second, and each one of those queries needs to be able to return its response in milliseconds. Otherwise, users will get fed up and they'll go to Yahoo or something. So from a search versus database perspective, these are kind of the two big technologies that you would think to power a web page or something like that has some dynamic content on it. And databases have a lot of advantages, right? That you can put data into them very easily, and when you ask for that data, it's immediately there. However, if you do a select against a very large database table, you may notice that that select or that SQL query could take a very long time. One of the reasons is because of this thing called a full table scan. If you're doing a select star from table where some criteria is true, it might actually have to iterate through every single row in that database table. And if you've got hundreds of millions or billions of rows in that database, you can imagine that end users will be waiting a long time and your website will never scale. Another thing is that databases are very good for being able to select or do an order or a sort on the result sets that come back. But one of the things that's built into search engines is the theory of information retrieval, which says that not only do we care about what records match your query, we want to know were the most interesting, which ones were the most relevant, the search results that match better than others, right? So you do have this concept of relevancy. Databases also typically have a very structured schema that if you have a database table, it has very explicit columns. Those columns in the database table have explicit types. Search engines tend to be more flexible than a database. And if we really think about it, in a way of speaking, the first search engine dates back to the ancient times in the Library of Alexandria, which is famous for having housed all of the world's knowledge prior to it burning down. As a matter of fact, any library that you go into has, or used to have, card catalogs. And what were these card catalogs? It was basically these big drawers where you can go in and you can look for a particular author, and then in there you had the list of all the books and the location in the library of where that author's books were. Or you could look up a particular topic. Fundamentally, a card catalog in a library is really the first search engine. As a matter of fact, the algorithm that powers a search engine is the same as what libraries used to make card catalogs. And what do we actually mean by that? Well, there's a data structure in a search engine called an inverted index, right? And this is probably the most important thing in a search engine, how it's structured. And it basically says that you want to add a document to the index. You want to add a document into the search engine. A document will have some sort of a unique identifier. We'll say document 1 or document 2. And those will have some associated text with them, some words, some things. But rather than inserting these as one row at a time, what you actually do in a search engine is you split up all of this text through a process called tokenization, where you take the individual words and you split these words up, and then you invert how it's organized. So we see that document 1 contains the word this. So I have a table that says the word this exists in both document 1 and document 2. The word is exists in document 1. A exists in both document 1 and document 2. Test, was, foo. So what you end up with is a way to address the documents that contain terms based on the terms in that document. So we're turning the data upside down. We're inverting how we're storing this data. So the data is stored based on the contents of it rather than the actual record itself. So this is what's referred to as an inverted index. And this is the reason why search engines are very fast, because it is pre-computing the answer to every one of your queries. So if I want to know what document contains the word foo, right? If I do a query, I type in foo, the answer is already pre-computed. The search engine already knows the answer before you even query for the term. So if you want to do a query for foo and the word a, for example, it only needs to create an intersection of these two result sets, right? Saying that only give me the documents that have a and foo. It has the list of all documents that contain a, and it has a list of all the documents that contain foo, and you can actually very quickly intersect these things. And that's how you can do these Boolean operations, to do and, or, and not. Those are your basic Boolean operators. So you can see that by structuring the data on disk like this, by creating this inverted index, all of a sudden now I can search for all these individual terms and get back the list of the documents immediately because they've already been computed. Let's see. there are a lot of search engines out there. There's a lot of commercial search engines. These are ones that people license. Historically, there was Alta Vista, another one called Verity. Verity was purchased by a company called Autonomy. Autonomy was purchased by Hewlett Packard. There was Fast Search and Transfer. They built a platform called Data Search, or ESP. They were purchased by Microsoft. Endeca was an e-commerce search platform. They were purchased by Oracle. Exalead was another search platform. They were purchased by Dassault Systems. Ativio is still around. They have not been purchased. MarkLogic is still around. They've not been purchased. Vivisimo was another search platform. They were purchased by IBM. So you can see that a lot of the search industry has evolved over time, and there's been a lot of acquisition in this space. One of the problems is that a lot of companies that I talk to now, they don't necessarily want to tie themselves into a commercial solution, because it's possible that their vendor might have been purchased, and whoever purchased the company might end of life the product and stop supporting them, or they'll change the licensing agreement so that the cost of that license is much more. So what I've seen is actually there's a big movement in the industry towards open source. So open source search solutions have evolved, and they are now as feature rich. They have as many features as the enterprise platforms typically did. So the kind of core of a lot of these is this library called Lucene. This is a library that was created by a man named Doug Cutting about, I don't know, I'd say 15 years ago. This was just basically a core API that allowed the creation and querying of the inverted index. Then was a company called CNET needed to wrap the Lucene library, so they created this platform called Solar. These are both Apache projects, so if you're familiar with the Apache Software Foundation, Solar and Lucene projects have been merged together as a top-level Apache projects. Solar says, what is it, server over Lucene with replication, SOLR. And this was created by a guy named Yannick Seeley at CNET, and open sourced. There's a pretty big community around this, where people are contributing to Solar very heavily, and kind of taking that and evolving that platform constantly. There was enough demand for Solar-based solutions that there's enough competition in the industry. Another company was created called Elasticsearch, and Elasticsearch, as a matter of fact, just built their own platform on top of Lucene. So from a functionality and technology perspective, both Solar and Elasticsearch are almost exactly the same. They just do things a little bit differently. At the end of the day, they are both based on top of Lucene. There are some other open source platforms for search. None of them are as popular as Solar or Elasticsearch. One's called Sphinx, and Sphinx has a very big integration into MySQL. There's another one called Xapien, MNO Go Search. And then for those of you out there who just like your Unix command line tools, you could always use grep. But predominantly, Lucene and Elasticsearch are the dominant players in open source search at this point. You know, the search engine itself is really just a core piece of technology that allows you to build and query the index, but it's often much more important to be able to get data into the index. You need to be able to connect to like a database, to crawl the database, to pull it in. Maybe you've got a web crawler that goes out and it spiders a website, downloads every single one of the pages, parses those pages, and puts them in. You may also need to do stuff where you scale up the size of your index. You might need to
Kevin, did you rejoin? Hold on, guys.
I'm sorry about that. Can you guys hear me again?
Yes.
Okay, I just crashed here. That's all. And can you still see my desktop? Maybe not.
Yeah.
I don't think it's actually refreshing though. You might need to make me presenter again.
Okay.
Yeah, thanks, George.
Are you a presenter now, or?
I should see it update because I'm on a different slide, so.
Okay.
Okay.
Are you presenter now?
I think so. Do you see the diagram? Search architecture.
Yes, now we do.
Okay. So one thing that we have here is kind of a traditional architecture for a search platform, where in the middle you have the search index. This is where the inverted index is. For this example, I'm just talking about Solr, but that could be any other search engine, Elasticsearch, or one of the commercial vendors like Ativio or Endeca, whatever. Typically on the left-hand side here, I write it out so as that you have the data source. The data source on the left-hand side, this could be a database, it could be a file system, it could be, some other, web service or something like that, some data source, some data repository, where you have a connector that typically goes through something called an index pipeline. And this pipeline has a series of stages. And each stage passes one document from each stage to the next stage. And each stage has the responsibility for doing things like parsing the HTML or adding metadata or extracting out people's names and things like that into structured information before it sends that document to Solr, where it gets indexed and becomes searchable. And then typically on the right-hand side is you have your web page, your user interface, and that will typically talk through some sort of like a REST API or like a web service layer that allows you to execute a query. You might do additional things to that query. It goes into the Solr index, and it comes back through a pipeline, and then ultimately return back to the web page so that you can render it in the user interface. So this is kind of just like a data flow, and it makes it modular so as that you can add new stages as you go. If you need to build a custom business logic in one of these places, you can kind of easily extend it, and it becomes hopefully very straightforward to add new features that clients are interested in. So if we look a little bit more at the Solr index itself and how we actually scale this up, this is a distributed platform. So you have things called shards and replicas. So if you want to scale up the number of documents you can index, you add an additional shard. So you're splitting the data across many machines. So that means that in this example here, 1/3 of the data is here, 1/3 of the data is here, 1/3 of the data is here. If you want to increase the number of documents, you add more machines going across the number of shards of the index. If you want to increase the number of concurrent users, the number of queries per second that you can serve, maybe you know that there's going to be a large spike in traffic, you create what's called a new replica. So basically, each one of these machines has a copy of itself. And then typically you would have like a load balancer that will take your queries and it will distribute the queries over each one of these rows. And anytime you want to do a search, you actually search across all three of these machines at the same time, or all three of these, or all three of these. So you can see that as you add documents to the index, what you're doing is you're going to be adding a document here, or here, or here, depending on some algorithm. And what you typically have is some sort of a unique identifier for your document. We call this a globally unique identifier. Hopefully it's deterministic and globally unique. This is a unique identifier that identifies each document in your index. And then typically what you'll do is using a hash or a hashing algorithm, something like a CRC32 or an MD5 checksum, you can actually determine which machine you want to send it to, and you'll get a random distribution of the documents across these machines. That'll allow you to scale up and route the documents across them all. Again, each one of those will get a replica so as that you can scale your query capacity if you need to. So one of the nice things is that built into a lot of these search engines, especially with Solr or Elasticsearch, is that it has built into it the ability to manage a cluster of machines. And if one of these machines goes down, you can still search, because as you scale up the number of machines, the likelihood that you have an error, one of the machines will crash, goes up. So the search cluster needs to be fault tolerant to that, right? If a machine is down, you still need to be able to search all of your content. So when that machine comes back up, the Solr index will be replicated from this machine to this machine, and you'll have all your machines back in service again. We talked a little bit about the ingest pipeline here. There's a lot of stuff that can happen there, which is, you know, you might have like a PDF file that you want to index, or a Word document, for example, or a web page. So really what you want to do when you're putting this into the index is you want to extract out of that document just the text. You don't give it the binary data. You want the text and the metadata properties. So the first thing that you could do is MIME type detection. Is it a PDF? Is it an HTML file? Is it a plain text file? And there's a very good library from Apache called Tika. Apache Tika is a library that you can use to convert many different file formats into text, and it will pull out for you all the metadata, the title, and just the raw text of the document. So when dealing with a lot of different types of documents, you want to ensure that they are all indexed and converted into UTF-8 typically, so as that you can support multiple languages and you know, multiple character sets. If you need to search in Japanese or Chinese or Korean, for example, you want to make sure that you're always using UTF-8 as your character set. You may be interested in doing different processing depending on what language it is, so maybe you do a statistical model to determine what language is this document. For example, Japanese, Chinese, and Korean text, they do not have spaces between their words. So the process of tokenization, where you're splitting up the text into individual words, is more difficult for those languages. You may be interested in scanning through that text, pulling out like the names of towns and cities and countries, people's names, things like that. So that's a process called entity extraction. And there's a lot of technologies for this. Stanford has OpenNLP, or Core NLP is another library, and these are very popular open source libraries for doing this natural language processing, where you pull out like key phrases, extraction of the concepts from it. Perhaps you're doing something where you are looking at what's called sentiment analysis. Let's say we're looking at movie reviews. Somebody says that they really love, you know, Star Wars, but they really did not like what's a bad movie? Attack of the Killer Tomatoes, right? So they love Star Wars, but they do not like Attack of the Killer Tomatoes. You might be able to do a statistical model that actually analyzes the text for the tone. Do they sound happy when they're saying this text, or they sound angry or something like that? You can assign a sentiment analysis to each one of the documents. Once all that text processing has been done and it goes into the index, then you can begin filtering on that. So if you want to say, you know, search for Star Wars, but only see the reviews where somebody liked it, right? So we can see that by enhancing the data before it goes into the search engine, now we can start asking those more interesting questions. I kind of went through that pretty quickly. I kind of wanted to, maybe open it up to some questions that maybe you have. I don't know if you guys have any questions. So I'm a contributor to the Solar project. I've contributed a few things to Solar. One of the things that I contributed was something called a graph query, which allows you to answer questions like friend of a friend. Who are my friend's friends? Things like that. So you can kind of use search engines to search things like social networks, to see who's linked to who, and actually understand that stuff. And I can talk about that for a little while if you're interested in that. And as George had mentioned, yes, there is a robot in the back room here. I don't know if my webcam is still turned on.
We cannot see you. Oh, now we do.
There it is, yeah. So you can see this is a life-sized humanoid 3D printed robot called the InMove. So anybody with a 3D printer can download all of the parts, 3D print that entire robot out, and the software that powers that is another package that I contribute to called My Robot Lab. This is a Java-based robotics framework for controlling robots, where it has built into it speech recognition, speech synthesis, chat robot. You can do servo motor control, computing things like how do you position the robot arm to grab something and things like that. We've also integrated into it for video processing, image recognition, facial detection, an open source project called OpenCV, which allows us to do things like object recognition in video, object tracking. So if you hold up a tennis ball or a ball, the robot can actually track where you're looking and follow, an object and look around at it. Yeah, I don't know. I think that the key is that enterprise software tends to be very expensive, and a lot of large companies will pay a lot of money for enterprise software. But open source software is a lot funner, and I think that it's becoming more important in the real world. And it's kind of amazing that if you are familiar with a lot of these different open source projects, you can build pretty much anything that you want. Especially now, some of the more interesting things that are coming out are the deep learning frameworks, right? Like deep learning for J or TensorFlow, and these are frameworks that allow you to do distributed computing to build artificial intelligence to create things called convolutional neural networks that allow you to do image recognition and classification for things like that. And there's a big move in the industry now towards this search combined with machine learning and artificial intelligence to create things like recommendation engines. So, things like, you bought this, you probably like that. How does Amazon decide that you should also purchase this other thing? Or, if you're looking at an image, does this image contain a person? Does it contain a boat or a car or whatever? And so a lot of these sort of machine learning algorithms now are being applied during the ingest pipeline stage here to tag the documents before they go into the index. So then if you want to do a search for show me all images that contain an apple, or show me all the images that contain a car or a boat, that becomes metadata that's associated with the records in the index, and you can start doing those sorts of queries. So by combining some of these technologies together and then having a very fast way to recall that data, to index it, to search it, I think is kind of where the industry is now and where it's going to be going for the next couple of years.
Thank you. That was very interesting. Can you hear me?
Yeah. You're very welcome. Spasiba.
I actually have a question
Yeah.
about, do they always save everything that you ever searched? Like, even if you mistype things like maybe
Right.
per bad, but you have typed BEP, for example. Do they have an algorithm to determine whether there was something that you intentionally searched or you mistyped, and do they save that?
Yeah. So anytime you execute a search against a search engine, they typically get logged into a file, right? So there's a similar to a web page that has its access log. A search engine will have its query logs, right? And the query logs will contain things like what did you search for, when did you search for it, what was your IP address when you searched, and then what they'll do afterwards is they'll go through those query logs and actually look at them to see, what searches returned 0 hits, right? If you mistyped something or misspelled something, the query logs will tell you what did you search for and how many searches were found. The search engines may also do something like you searched for something and then you clicked on hit number 4. They might track that as well. This is called click-through tracking. So they'll track what you click on, and then maybe the next time you do a search, they'll use that information to boost that document in the results set, because you want to make that document come up higher, because if they searched for something and then they clicked on this document, there's a good indication that those two things are related to each other. So this is what's referred to as adaptive relevancy. So is that the search engine over time, when users are interacting with it, will actually provide feedback into the relevancy and the ranking algorithm, so is that the search results that are commonly clicked on will come up higher in the result set.
Are they planning ever to delete the stuff that was outdated, like that you searched for 10 years ago, or they want to save everything for all of the times?
Well, I think Google has a lot of hard drives, so they can store a lot of data. I think this is an old number, maybe about like 5 years ago or so. Google had something like 250,000 servers that powered their search engine. I think it's probably close to 1 million servers now. So they have a lot of storage to store this information. They make a lot of this data actually available to people that perhaps they're interested in doing some machine learning on top of it. So I suspect that a lot of these companies, they save this information for a very long time. But they can't always tie it back to you. They might not know exactly who was searching, but they definitely know what was searched for. So that way they can actually say the most popular term that was searched 5 years ago was this, whereas the most popular term today is that. So they can do these sort of what are the most popular query terms over time sort of things. And that's all based off of these query logs.
Thank you.
Hi, Kevin. We have a question from the chat from Dimitri.
Sure. Hi, Dimitri.
Could you review it, please? There's a long text.
I'm sorry. What was that you asked?
There is a question in the chat.
Oh, yeah. Found Elastic Cloud. Yes. So let me see. One moment. What are your thoughts on Angola? It sounds familiar. Let me take a quick look here. I came across it once. This is a hosted search service that I think they actually. Oh, right. I think that this is just a web-based or a hosted Elasticsearch index. I think, Dimitri, you actually found that. So if you want, one of the things is if you're running a big search engine in a cluster, you might not want to be woken up at 2 in the morning if a server goes down, right? So it's a real pain to fix servers. So a lot of times companies will actually outsource the hosting of this to, like Amazon, and then they'll have somebody manage those clusters to make sure that they don't run out of disk space. I'm sorry, what was that, George?
No, it's just a noise.
Okay, so there are some companies that will host the solution for you, so you don't have to worry about getting woken up at like 2 in the morning if something breaks. Typically, these services like Angola, there's another one called Measured Search that hosts search solutions. Search Technologies is another company that will do that for you. And these are really just companies that expose or put a wrapper around either Elasticsearch or Solr. So you can download it, you can build your own, you don't necessarily need them to host that for you. All of the technology that they have is exactly the same as Elasticsearch or Solr. So it's just a question of who's going to manage the servers for you.
I have a question.
Yes.
Another
question. My question is, so what would you choose, Elastic or Solr, and why?
My preference is Solr. It's been around longer, and but from a functionality perspective, they both do something very similar. One of the things that I like Solr for is I am the author of the graph query, which is part of Solr, so I'm biased, right? Like I prefer Solr for that, and I know many of the contributors and committers to the Solr project. I've gone out and had beers with them on many occasions. So I like Solr better than Elastic, but they both do exactly the same thing. They both have very high performance. They are both based on Lucene. So from a technical perspective, they are very similar. Elasticsearch is probably easier to get going from the beginning, and it's very JSON web service friendly. That all of their APIs are all basically JSON APIs and stuff. But there's no administration GUI for it, whereas Solr does have like a GUI where you can go and actually look at the health of a cluster. With Elasticsearch, you have to use like a JSON-based REST API to get the cluster health. So yeah, my preference is Solr. Elasticsearch is actually powered by a commercial company called Elasticsearch. So there is actually a business and a company that is employed to support Elasticsearch. The only people that can commit code into Elasticsearch work at Elasticsearch. So even though it is open source, the only people that contribute to that project work for the company. Whereas Solr is truly much more of an open source community where you have contributors from hundreds of different companies like Bloomberg and Cloudera and many other companies that support and contribute code to Solr. So I like that there is a larger diversity of companies that contribute to Solr, whereas Elasticsearch, only the people that work at Elasticsearch contribute to it. They're both open source, and they are both built on Lucene, but I feel like Solr is more open source than Elasticsearch because the contributors come from a lot of different places.
Thank you.
Yeah, okay. Any other questions? I speak very fast sometimes, so I apologize if I was speaking very quickly.
No, it's not that I have questions. It's just they are shy. Okay, that's the reason. So, guys, any other questions? Don't be shy. All right. Well,
I would encourage you to take a look at either Solar or Elasticsearch. They're fairly easy to get started. There's a lot of nice tutorials online. If you are ever finding yourself where you need to build a very scalable solution website or something that needs to have millions and millions of pieces of content, and you want to make sure that it can support thousands of users using it at the same time, then using a search engine as the basis for that is a very good idea, and it will make sure that your web page stays up and running and can scale. And for those who are interested in robotics and 3D printing, I would recommend taking a look at both InMove and the My Robot Lab projects if you're interested in that stuff.
I will share your account with the guys. Well, actually, they do have a LinkedIn account.
Sure.
So the people who will be interested in robotics, I'm sure they will.
Yeah, sure.
Yeah.
We can even do another presentation where we talk about My Robot Lab and Move as projects at some point in the future.
Cool.
And if anybody has any questions, they're kind of curious about search engines, you want to know more about it, or you're curious about My Robot Lab, then feel free to send me an email. I'm happy to talk about it.
Thank you very much.
Okay. Thank you very much.
Thanks a lot. We really appreciate your time.
Yeah, absolutely, absolutely. До свидания.
До свидания.